All right, how's everything going?
Good.
Question.
For different fonts.
Okay.
Really quick. For 215, are you going to change PA2 at all, or are you going to leave it the way it is?
I think it's the way it is.
All right, cool.
Yeah. But the PDF asks you to generate 500 even numbers, and the Canvas page said 100, so I changed that to 500. So you do what the PDF says, but that should match the Canvas page now. I may get back to doing some ODPs this week, I'm not sure. But all right, so PA3 is graded and commented and done, and most people seem to be pretty successful with PA3. So there's the hash stuff and the linked list stuff and all those low-level details, and actually that's not where most people lost points. Most of the lost points were more in the main program. Memory leaks and value grind issues, which, you know, are just kind of something to deal with. Not a whole lot of those going on, though. I was pretty happy, because particularly those errors that you get from value grind that aren't memory leaks, but that it's warning you about uninitialized stuff, those can be really tricky to get rid of. If you get rid of them as you're developing your code, it's easier than, you know, having the whole finished thing and then running value grind for the first time and finding them. But most people seem to have gotten rid of those, which is good. Commenting is looking good. Coding style is looking good. So keep developing those. And if you have, you know, concerns from your feedback or your grade, definitely come and talk to me. But I was happy with what I saw across the board. And then PA4, of course, you know, we can reuse a lot of the main program, because it's the same basic interface, slightly different command set, but as a wrapper to call your other functions, it's mostly reusable. So questions on anything up to this point? So I want to keep talking about trees and developing some of this tree code. Where are we going this week? So I want to talk about insert, search. We started these last week, but I want to go through them more carefully. I want to talk about height, and we need to talk about balance, which we haven't really talked about yet. Working up to deletion from a tree, and deletion is a more complex algorithm than these others. Insert, search, traversal, which we talked about in more detail last week. And then eventually I want to talk about another form of traversal that I'm not asking you to code, but something called breadth first traversal or breadth first search, where we basically move across the tree and we go deeper as we move across. So we print out the root first and then we just go down one level at a time. But that's going to need us to talk about queues. And towards the end of this whole discussion, we'll talk about something called AVL trees. This is a way to balance a tree, and once we talk about balance, we'll be able to talk about how we make a tree balanced and why we care about doing that. And I'm not planning to have you code up AVL trees, but it's a fun thing to code. So I might put it in somewhere. So this is, you know, at least this week worth of lecture to get through trees. We're in week 7 right now, so after this week we got 3 weeks left. And I wanted to talk about tries, which are like a fancy form of a tree. I want to talk about tries. I want to talk about dynamic programming and more recursion heavy concepts. And I want to talk about some algorithms like Dijkstra's algorithm for finding shortest path, which means talking about graph theory. I'd like to talk about sorting and searching in general, because we mostly do bubble sort, or I use bubble sort if I want a quick sort. There's lots of other sorting algorithms, so I want to talk about those, and that's going to be in another week. So probably this week on trees, maybe a little bit next week, and then we'll move on. And PA5 will probably be a dynamic programming project, and it'll probably be a group project. So you get to work in teams for that one. All right, so let's continue with trees. Right, so depth of a node is how many hops away it is from the root. And then the height of the tree is the depth of the deepest node. And we touched on this observation last week that if we want to find the height of a tree, we can simply find the height of the left and the right subtrees. And whichever one is largest, add 1 to that. That'll be the height of the original tree. All right, so height of a tree equals 1 plus the maximum of the height of the left subtree and the height of the right subtree. So that's a recursive definition, but if we're writing a height function, we can do that as long as we have a way to not recurse infinitely. If we just do this, we're going to keep trying to find the height of subtrees and subtrees, but eventually tree will be null, and when we look for the left subtree, we'll segfault. So it's this: if tree is not null. It's -1 if tree is null. So there's a good recursive definition of height that won't blow up. And height is just, how far down you might have to go to get to some node in your tree. Okay, so it's got a fairly good intuitive, if you draw your graph on paper, your tree on paper, it's, how tall it is. Okay, let's talk about balance. This will be a definition. So a tree T is called balanced if and only if one of the following is true. Possibility 1. T is null. So an empty tree is considered balanced. Or maybe more precisely, an empty tree is not considered unbalanced because there's no nodes in it. So we think of an empty tree is balanced. Or case 2, all 3 of these conditions are true. 1. The left subtree of T is balanced. 2. The right subtree of T is balanced. And 3. The absolute value of the height of those subtrees is no greater than 1. All All right, so tree is balanced two ways. First way, tree is empty. That's sort of the base case. The other way a tree can balance is if all three of these things are true, all three have to be true. Okay, this is worth an important flash, because I'll get code from people and they'll only check one of these three conditions and they'll say, yeah, your tree is balanced. Okay, all three of these things have to be true. The left subtree has to be balanced, the right subtree has to be balanced, and the heights of those left and right subtrees have to be within one of each other. Okay, if all three of those are true, you can say the tree is balanced. If the tree was null to begin with, you can say it's balanced. Otherwise, it's unbalanced. Is that clear? Yeah.
So is being balanced like a Boolean thing? Is it either
It's either balanced or not balanced. Yeah.
can be like 90% balanced?
We can measure how badly unbalanced it is, right? But this definition is Boolean, right? Otherwise, T is not balanced. So let's look at what balanced trees look like. We don't need to understand balance any more than this, though. If we have this definition, we can write a code that'll tell us if a tree is balanced. Well, let's just take a look at some trees and see what this looks like. So a null tree is balanced. A node containing a single root, well, it's not null, but we can check these three conditions. Is the left subtree balanced? Well, what's the left subtree? It's null. That's balanced. The right subtree is also null. That's balanced. The height of the left subtree is the height of an empty tree. That's -1. The height of the right subtree is -1. -1 and -1, those are within one of each other. So this single noded tree satisfies all three conditions. This is balanced. What about this tree? Two nodes, one's the root, the other one is a child on the left. Is this tree balanced? So what rule is being violated?
So the left node is balanced, but the right node isn't.
So the right node is the empty tree, right? And an empty tree is balanced.
But the right, like it doesn't have one.
So we're looking at a tree T, right? And we need its right subtree to be balanced. Well, the right subtree of this tree, this node is null, right? It's an empty, it's the same as what the right subtree of this node was, right? So we can think of this as null. We just don't usually draw them. But the right subtree is null, which is balanced. The left subtree is a single node, which we already decided was balanced. The height of this left subtree is what? Pretty close to 1.
0.
0. All right. Distance from the root to any node is 0, because there's just a root. So the height of this is 0. The height of a null tree, -1, right? -1 and 0 are within one of each other, so it satisfies all three conditions. So this is balanced. And let me throw down the height here. Okay, similarly, if I only have a node hanging off to the right, it's still going to be balanced, right? It's symmetric. Yeah. I'm not going to get in the habit of drawing these, though. But we want to know they're there, yeah. So the height of this tree and the height of that tree have to be within one of each other. Right, this has height 0, this has height -1, they differ by 1. That's legal. But let's look at this. So now the left subtree, that's still balanced, right? That's a balanced tree. The right subtree is null, that's a balanced tree. But we got a third condition, we have to compare the height of the left and right subtrees. Well, the left subtree looks like this, that has a height of 1. The right subtree is null, that has a height of -1. 1 and -1 differ by 2, it's not balanced. Alright, so this is not balanced. because the heights differ by more than 1. What about this tree? That was pretty fast. Yes, it is balanced. So the left subtree is balanced, right? The right subtree is balanced. The height of this is 1, the height of this is 0. That's within 1. This is balanced. And this also has a height of 2. Right, this is going to be balanced as well, because that's a balanced tree, that's a balanced tree, that has a height of 1, that has a height of 1, satisfies all the requirements, that's balanced. Is this a balanced tree? Are you sure? So first the left subtree has to be balanced. Is that balanced? All right, we already decided that was not balanced. So right there we can stop and we can say this is not balanced. And that's a good thing, because if we just look at the heights, the left and right subtrees have exactly the same height. But it would be kind of bizarre if this was considered a balanced tree, because that's like the most unbalanced tree in the world. So is that, and we've just taken 2 of these and put them together, right? It's balanced in the physics sense, right? But not in the binary tree sense. And it will fail the balance test because the left subtree is definitely not going to be balanced. Because if you just look at this tree, this is what the left subtree looks like, the right subtree is null. Those differ radically in height. So this is definitely not balanced. So our intuition is not always going to be reliable, right? For example, this might not look balanced to us, but it is. And this may look balanced, but it's not. So what is balance trying to capture? It's trying to capture the idea that as you fill in elements on this tree, you're filling in as much across as possible before you move down. And I have all of these nulls hanging out here that, you know, could have values in them without changing the height of the tree. But we're not using these. We made the tree taller without making it as full as possible. So usually a balanced tree, we're filling things in at the higher levels, the lower depths, before we move down. Right? So that's the main reason this is such an unbalanced tree, is that we could have put some nodes here, and we could have put some more nodes under that, and we could have filled in a whole bunch of nodes. This has 7 nodes along this path. Right? That's enough for 127 nodes in our tree. And if we've only put in 7 nodes in that size tree, we've got a lot of empty space. So balanced tree kind of means we don't have a lot of empty space at the higher levels. Okay, and why do we care about balance? Because all of our algorithms for dealing with trees are going to be recursive. They're going to basically start off with the root of a tree, and they're going to take some action based on something happening in either the left or the right subtree. Every time we make this recursive call, we're going to go down one level deeper in our original tree. The height of our tree is basically how many times we're going to have to make these recursive calls. Because usually we end when we get to a leaf node. So if I have 4 billion things I want to put in my tree, I can do that with a tree with height 32. 32 recursive calls, I can do whatever I want to do in that tree with 4 billion nodes. But if I make a tree that looks like this with 4 billion nodes, it's going to have 4 billion things in a line, I might have to make 4 billion recursive calls to get to the last node. Okay, so it's an efficiency thing. If our tree is radically unbalanced, a lot of our algorithms will be order n, where n is how many things we have in the tree. If it's a well-balanced tree, it'll usually be order log n. Log base 2. Log n's a really nice order. Right, it takes you from 4 billion down to 32. So this is a nice recursive definition, and we can actually code a balance function just following this. So balance, struct node t, if t equals null, return 0. If balance t arrow left equals 0, return 0. If balance t arrow right equals 0, return 0, right? Because one of those is not balanced. Otherwise, if the absolute value of height t arrow left minus height t arrow right is bigger than 1, return 0. Otherwise, return 1, saying we're balanced. Different ways you can phrase those conditions, but that's the essence of our balance function. Right, see if it's null, make 2 recursive calls to balance, make 2 calls to height. But along the way, if any of these fail, you can immediately kick out and say it's not balanced. So for PA4, you need to code a balance function. And it's, that many lines. The balance function you're writing, so when you're done writing it, you'll have a balance function you can call. The height function you're also going to need to write, and you're going to want to write that first. And we coded up pseudocode for a height function, right? Height function is -1 if the tree is null, otherwise it's 1 plus the largest of the heights of the left and right subtree.
Is inserting an ABL tree long in still?
Yeah. Yeah, it's the same as inserting in a regular tree, and then you have an order 1 operation to do. Well,
You kind of just like pivot the tree.
you basically just pivot, yeah.
And add maybe like a null somewhere else.
Yeah.
Okay.
You might have to go up to find a pivot point, but that's no worse than log n. So it's still log n overall. Same with deleting.
Is it okay if we make our tree self-balancing for this for PA4? If you want?
Not if you want points.
Not at all.
Yeah. You could make a separate delete function, right? Like bdelete or something that'll delete and rebalance. Yeah, that wouldn't work for insert. I mean, you could make a different version of your program if you want to.
So it's okay if we don't do it, just do it somewhere else.
Yeah. But yeah, I'm going to be running with sample databases and looking at exactly what your tree looks like. But make a different version if you want, and I'll be happy to look at that because it's a fun thing to code. Yeah.
So like in real life scenarios, like when you do have trees, do people prefer that you make it self-balancing? Or is that
Yeah, I mean, you'd like to have balanced trees because you want to keep your efficiency up, and if you're taking data in that happens to be alphabetized and you build a tree out of it, you get a big long list, and it's horrible. But in real life, you're just using a tree package from somewhere, right? It's pretty rare that you would actually be coding a bare tree package yourself. You might start with someone's tree package and then, extend it to be a tree of hashes or something like that. But you would have all the machinery that came with that. Yeah, it's kind of weird. We take courses and we learn how to code these things, and we don't actually do those in real life. But, the goal is not to learn how to code a tree algorithm. The goal is to understand trees and understand the code that manipulates them, so that whatever code we do have to write, we're comfortable with. So it's kind of a interesting setup. But if you teach computer science someday, you will have to write tree code. I can attest to that personally. All right. Let's take another look at insert. And I'll just stick with integers here. So remember, all of our tree functions we're going to want to return usually a struct node star if we're making any changes to the tree, so that we can, potentially change the root of our tree. So if t is null, if the tree is null to begin with, just make a new node and return that as the root of the tree. That's our edge case. So that's an empty tree. Otherwise, we have at least a root node, which means we can decide if we're going to insert on the left or right subtree of the root. So if our number is less than the root node's value, and in that case we just recurse and we say, let's call our insert function on the left subtree and ask it to insert data into that left subtree. We know that's the correct tree to insert in because our number is less than the root. And this will return a new copy of the left subtree. So let's say our tree originally looked like this. And we're saying insert. Let's insert a 12. Okay, what this call is going to do is it's going to take the left subtree. It's going to insert a 12 into it, which means it's going to turn into something like this. And insert's going to return this root. And we're going to take the original root node and change its left subtree to be whatever insert returned. So that's going to set 20 to point to this. So now we got 20, 10, 5, 15, 12. We have to do that for the following reason. What's the head? 5 and 15. Suppose I say insert 18. So I'm going to say let's insert, oh actually I don't think I need to do that. Nope. Okay, don't worry about it. We'll talk about it when we get to delete. Suppose this is our original tree T, and we want to insert an 18 into here. Okay, this is going to say insert an 18 into T's left subchild. Well, T's left subchild is null. Right, there's nothing to the left. Right, 18 is less than 20, so we want to insert to the left. There's nothing in the left subtree, so we're going to make a call to insert into a null tree the number 18. Well, that call to insert is going to say, okay, my tree is null, let's just make a new node 18 and return that. So the return value from this is going to be just a single node containing 18. If we don't do anything with that, right, we haven't changed our original tree. The correct thing to do is to change T's left child to point to that new node. Okay, that's the point of this statement. So if we're not changing the root of this left child, this really doesn't do anything, right? It just makes some change in here. But if we actually need to change the root, we need to make sure T arrow left equals whatever insert returns. So in that case, that would make our tree look like this. And there's your new node. All right, so if our number is smaller than the root data, insert into the left subtree and change T left to be that new subtree. All right, else, let's assume it's on the right, T right equals insert T right data. And then when we're done, we're supposed to return the root of the new tree that's still going to be T. So we just return T. So that lets you add nodes to a tree. And if you put that together with the traversal, right, you've got a big chunk of PA4 and a big enough chunk that you can work with it effectively, make yourself some small databases, do some traversal, and get all that stuff nailed down, and then you can move on to search.
When I was writing this last night, I had a thought, a question about recursion. So if you did it wrong, say, and you didn't actually return the T rights, and so you're just calling insert, just returning multiple times, does that throw a runtime error, or what actually happened? Or will your compiler just take the very last return and set that equal? So say you said root equals, you'll just take the very last return and...
You'll take the last return, yeah.
So it just discards previous returns that aren't used?
Yeah, if you return a value and you don't do anything with it, it doesn't cause any harm.
Okay. Is that considered bad practice to do something like that, or is that done?
There's times when you might want to do that. For example, you want to execute a call to a function and it can return an error condition, but you're really sure that that error condition is not going to happen, right? You may not care about it. Like scanf, you don't have to check the return value, but we usually do. Like string copy, let's see. Right, so string copy returns a pointer to the destination string, right? We usually don't use that. We're usually just saying copy from source into destination, and so we just ignore that return value. But if you wanted to do something with it, right, you don't have to save, you don't have to make an extra statement to do something with the destination.
Yeah, I understand that. I was just curious about if doing it recursively is exactly the same, totally fine, or if there's problems that would arise if you're doing something like that, or if, like, are there common recursive algorithms that use something like that, where they only use the last return and just
I don't think so. My brain is thinking like every time that you do recursion, you need to be using that return value all the time. Because you're trying to build something up, basically. And if you don't pass it up from the bottom, why did you go all the way down to the bottom?
Yeah, what's useful?
But then we're starting to get into a debate about functional programming, which would be a fun debate or discussion. All right. So sample database to work with. Let's make ourselves a little tree that looks like this. Because you want to test your traversal orders. Let's make a 20, 10, 30. Okay, how do we cause this tree to be built in memory in PA4? Well, first insert a 20 and then a 10 and then a 30. Right, 20 will become the root. The first thing you put into your database will always be the root, and then a 10 will go to the left, and then a 30 will go to the right. So if I input data in this order to build my tree, this should be what the tree looks like. Okay, so I'm going to make a new database. My license plate is going to be 20. I'm going to call this root, and my next database, my next license plate is going to be 10, and I'll call this left, left, and then 30 will be right, right. They're not license plates, I don't care, right? I don't have to do what my program expects me to do, but it has to do what I expect it to do. So let's run plate 4 on this small database, data.txt, and let's say dump. Okay, so my left node right traversal shows me 10, 20, 30. That's what I was hoping for. I was hoping this was going to come out in sorted order. And if you look at this original tree, left node right is going to say go to the left first, that's a 10, then print out the root node, and then print out the right child. If I do node left right, that says print the root node first, then go to the left, and then go to the right. And if I go left right node, that means traverse all the way to the left first, and then traverse to the right, and then print out the root node. So LNR, that's called in order, that should be 10, 20, 30. Node first should be 20, 10, 30. Node last should be 10, 30, 20. Right? Which is what we're seeing here. So you can kind of sanity check your traversal on small trees. Just make your own license plate database with you know, something more meaningful as far as order, and make sure those traversals are doing the right thing. And by the way, the height is 1, balance factor, yes. That's just one of these trees. We didn't even do that one. It's like the most beautiful tree in the world. This one is definitely going to be balanced. And a height of 1 node to the root. So if you want to check this tree, which should not be balanced, has a height of 2, we want to build a tree where everything goes off to the left. Well, one way to do that is input a 20, and then a 10, and then a 5. That should make my tree look like that. Alright, so 20 will be the root, and then 10 will be to the left of that, and then 5 should be even more to the left of that. Alright, so that a major fail. Okay. So the tree has a height of 2, it's not balanced. The in-order traversal is 5, 10, 20 as we expect. The NLR is 20, 10, 5. Why? Because we're saying first visit the node and then go to the left. So we print the 20. Now we traverse this tree in node left right, which means print the node, which is 10, and then traverse the left subtree in node left right, which is a 5. So we get a 20, 10, 5. And if we go left right node, that means go all the way to the left, which is a 5, and then all the way to the right while there's nothing on the right, and then do the root node. Do that, go to the right of the 20, and then do the root. So the left right node happens to come out in the same as the in order left node right. So make yourself simple database files and play around with your code to make sure that the code works, and also to just get yourself more and more familiar with traversing trees and building trees and calculating these things by hand, right? What's the height, what's the balance factor, and so on and so forth. And I had to make it a 0.5 because it's still alphabetizing based on license plate, right? So I wanted 0.5 to be smaller than 10. So recursion is a powerful way to code. It can be used when it maybe shouldn't be. We can start to think of lots of things recursively. For example, how many coins do I have in my hand? Right, I want to count it. Well, I can put it on the table and go 1, 2, 3, 4, 5, right? How could I do this recursively? I could say if my hand is empty, the answer is 0. Okay. Otherwise, I take out one coin and I write down on a piece of paper, I had one coin in my hand, and now I hand the rest of my coins to a friend and I say, tell me how many coins I have. They give me back an answer n. I add 1 to that, that's how many coins I originally had. And there's no looping. It's just if my hand is empty, I have no coins. Otherwise, I have 1 coin plus however many coins my friend says when I hand them the remaining coins in my hand. And my friend, of course, is myself, so I just call myself with 1 less coin to start with, add 1 to the answer, that's how many coins I had. So you want to write something that finds the length of a string, same idea. If character 0 is the null terminator, return a 0, otherwise call yourself with a string that starts at character 1, take the result from that, add 1 to it, and you're done.
When a loop would be just as easy.
Yeah.
I consider bad practice to use recursion because it's less readable.
It's bad practice to use recursion, I think, unless you really need to. And that's a subjective thing.
Or your functional programming.
Yeah. So in the case of string length, if somebody handed you a string 1,000 characters long, you'd be recursing 1,000 times deep. That's not a good thing to do.
Yeah.
Right? You're in danger of stack issues. If it's something where your recursion is only going to go a few levels deep, I don't think there's anything wrong with it, unless it's going to be grossly inefficient. But you know, if it's a job interview, it's worth mentioning both. It's like, well, I could do this recursively in 3 lines, but it wouldn't be, you know, it might be overkill or something. So here's a case where recursion does not need to be applied, but it was fun to write anyway. So here's a mini linked list package, right? I have our standard struct node, I have our prototype functions for adding and printing. I don't have search or delete in here, but I want to add things to my linked list in the right spot so that my list is in increasing order. And I'm driving this with some test code where I start off with my list is null. So I've gotten rid of my sentinel node here, because sentinels don't work well with recursion. So my empty list is null. And so when I add something to a list, I take the return value and I set list equal to that. So I'm just adding some data to my list, 10, 5, 20, 40, negative 20, 17, negative 10, 15. Okay, all jumbled up. And when I run this and I ask it to print my list, all the data is in sorted order, as you can see. So my insert, my add function is putting things not just at the beginning, but in the correct place. What does my add function actually look like? It's this. If the list is empty, I just make a new node and I return that. Okay, that's the base case, if you like. Here's the real work happening. If the data is smaller than the first thing in the list, I make a new node. I have that node point to the original list, and I return that new node as the start of the list. Okay, so this is the case where we're inserting in the beginning. Here's the case where we're not inserting in the beginning, where we have to insert somewhere down the list. And it's a single recursive call. I basically say, let's use the add function to insert my data in the remainder of the list. And then let's have my first node of the list point to that new list into which I've inserted a new node. So there's no previous current, there's no moving through and keeping track of things and looping until this thing is null and so on and so forth, right? The intuition here is, here's my list, here's a number I want to add. If it goes right in the beginning, I know how to do that. Otherwise, let's take off the first thing in the list, take the remainder of the list, hand it to someone, say, insert my number into this list. They give me the list back, I just point to that from the first node, and we're done. And then traversal is simple. If the list is empty, we just print out a new line. Otherwise, print the first node's data, and then print the rest of the list. Right, I print the first node's data with a printf, I print the rest of the list by calling my print function. Right? That's like about as simple as you could hope. Now that's recursive, and for a long list, it's not necessarily what you want to do. But it's an interesting way to think about tasks. Right? And we're thinking about doing a task by doing some subtask, and then doing some little piece of work, usually before or after. And that's going to be a heavy theme in PA5. It's going to be all about thinking about subtasks of larger tasks. Here's a simpler version where I allowed my new node function to take not just a piece of data, but also the value that you want it to point to. And here's my entire add function for adding into a list. If the list is null or goes in the beginning, make a new node, have it point to the current value of list. Otherwise, add my data to the remainder of the list, and have my first node point to that. So this is a different but really powerful way to think about algorithms. All right, so we'll look at search again tomorrow, and then I want to start talking about deletion from trees. All right, I will see you tomorrow.